Well, actually, thank you very much for having me here. I will a little bit talk about finance first, so it's more like a vertical talk. I won't talk about some fancy new libraries or new functions. What we use in our daily business is more or less common stuff that almost anybody who is using Python in a scientific context is using. So before I start, I introduce myself with a couple of sentences and with the topic. I want to ask the auditorium who has a finance background, who is from a bank or insurance company, or who has studied finance some time ago. Oh, it's the minority. So I brought a little bit of theory with me just to illustrate what we are doing. So if you don't understand the theory that I will present, it doesn't matter that much. The point that I will make today is that many people think that Python is not well suited to build high-performing financial applications because it's an interpreted language and all that kind of stuff. So the main point that I will do is that it's very well suited, and the very proof is that we built really off-the-shelf valuation suite by ourselves, so we are distributing it, and we are more on the application side and not on the developer side. So to say, I'm not the developer at all. I'm just a quant, so to say. I'm prototyping in Python, and we have guys that are the real developers that have to take care of the productive environments. So I'm more at the interface between theory and practice in terms of Python. So let's start with me. I have a background in business administration. I studied business administration and then wrote my PhD thesis about mathematical finance topic. After that, I started working as a management consulting with a more broader focus. I consulted mainly insurance companies, also banks, and founded a company on my own in 2005 where we use Python extensively from the beginning on. So we bet on Python at a time when nobody else in the financial services industry was using Python for the things that we use, but a little bit on that later on. What I also do is I give a course at the University of Saarland, the German university, where we also use Python. And I found it very, very useful to apply Python in such a context because people who are not developing or programming experts really fast can grasp what's behind it because it's quite compact and readable, and it mainly looks like mathematics. So I will present it later on. I'm also writing a book currently where I use extensively Python. It's a financial book, but the implementations are all presented in Pythonian language. What about the topics for today? So first I will start with a couple of slides about derivatives analytics in general and why Python. I will then proceed and talk a little bit about data analysis. This is not our main focus, but what our focus is Monte Carlo simulation, which is computationally very demanding and where you need pretty fast implementations to get by on a daily basis. And last but not least, a couple of slides and maybe some presentations in terms of an Excel sheet or a Python script or even the application, if the Wi-Fi works, of our decision analytics suite. But let's just dive into it. Derivatives analytics. First of all, does everybody know what an option is? A couple of people know what an option is. You probably almost heard of stocks, which are traded at exchanges. And these are like ordinary securities. But there are other securities that derive their value from these ordinary securities. In terms of an option, for example, you can buy the right to sell, for example, then you speak of a put, the stock at a predetermined date in the future at a predetermined price. So you have the right but not the obligation to do so, and it's a derivative, it's a security that is traded that derives the value from another security. These are hard to value. It took a couple of time, and it was not long ago that the first paper in this regard was published in 1973 in terms of science. It's not long ago, but since then, around this concept, there has been built a multi-billion-dollar business, and latest since the last financial crisis, everybody will heard of these derivatives as financial weapons of mass destruction, as Warren Buffett called them, because they were blamed, to some extent at least, to have caused the recent financial crisis. But today this is not our topic. It's more like how you handle these in terms of technology. Typical tasks in the context of derivatives analytics are to simulate something, to analyze data, to do some discounting in the financial context, to have arithmetic operations. You want to sum up things. For example, if you have a portfolio, you want to average something. You have to calculate, for example, average returns. You have a lot of linear algebra in that, in finance theory. You can say finance theory is all about linear algebra. All what you do is can be represented by matrices and vectors, which translates into Python and Numpy arrays, which I will present later on. You have, of course, some optimization problems. People want to reach the optimum for a given investment. You have also, of course, some visualization things. And if you take a look at the list, these are all tasks that Python is quite good at. But still, C, C++, C#, MATLAB, and all the other languages that you are very well aware of still dominate the industry. But Python is coming. I will present some figures about that shortly. Why Python? Here on this slide I have two perspectives. The one perspective is from a business point of view. The other is also for people who want to get into finance or who want to learn all the things that I'm talking about. And the first, of course, is open source. For the big banks that make billions of money with this kind of thing, open source in terms of low cost, maybe not the reason, but for a student who's learning finance, it could of course be a reason to choose Python and not to invest like €1,000 for a license of MATLAB, for example. The syntax, Python program is easy, you know that, but from a business point of view, you also have the advantage that you can develop fast, and the second point is even more important, you have easy maintenance. You have lots of legacy code today in financial industry companies that no one even understands anymore. You have thousands of lines of codes for single modules and no one is capable of maintaining these things, and they have built their business around these things. So Python could help in replace these with some more readable code. And all the other kinds of things. But the last point, maybe the most important on this slide, many people still think that Python is not fast enough for a couple of financial applications, but that's not the case if you do it right. If you use Numpy, for example, you know that you can have mathematics at the speed of C code, but maybe with only 5 lines of code where you would need like 500 lines of code if you want to implement it in C. So you have a major advantage in this regard. What does the financial market says about this? Because this was more like a theoretical view on it. I just looked at the website where they report the Python contract offerings in the London area, where they are looking for Python contract developers. And it's more or less for the first quarter of this year, where we observed 644 offerings with regard to Python skills. And only 2 years ago, the comparable figure was only 142. So there's today a fourfold demand for the Python skill in the London area, which is mainly financially driven compared to 2 years. This is an amazing growth. And the money you can earn with it also increased a little bit. But you see more and more financial services companies are employing Python, and not only for the cluster stuff and the managing stuff, but also for the core applications that they're implementing and using. And especially companies that are a little bit smaller and they're coming new to the market and they have the choice and have not much legacy code, of course. They can say, we start out with Python and we do it right away. Others are a little bit more reluctant when they have a huge library in C++, then they may stick a little bit longer to that. But Python is catching up at a rapid pace in the financial services industry. But now, let us go into the topic of the talk, derivatives analytics. And a major part of analytics is, of course, data analysis. If we speak in finance of data analysis, there are mainly 2 types of data that we want to analyze. The first are time series. If you observe a stock over a period of time, you have different values attached to different points in times, but you also have cross-sections that you want to analyze. It's like you have a single date and you have different data for this single date. And these are, it's a little bit simplifying, but these are the 2 main data types that you want to analyze, and there are a number of very useful libraries. I listed just 4 of them. XLRD, just to get access to information which is stored as an Excel file. Many of you would say, who want to store data in Excel files? But in the financial services industry, it is the case that most of the people are still using Excel. It is as it is. So on every trader's desk or a quant's desk, you will find Excel files. And even if you want to do something for yourself and you go to Yahoo, for example, you can download stock data, for example, as an Excel file. So it's very useful to have something to get access to data stored in an Excel file. And XLRD, for example, makes it very convenient. There are a number of others, but you can use this. Numpy, of course, it's the core to have fast data crunching. But Pandas is also a very useful extension of Numpy, where time series analysis is added. For example, if you have a time series which is not like evenly distributed over the year, where you have like one date at the beginning of the month, you have a second one, and for next month you have 10 dates and so forth. Pandas takes care of all these. And there's also, if you have a 3 time series, for example, Pandas can analyze these simultaneously and, for example, handle missing data. Because if you have 2 time series where you have data not for the same points in time, then what do you do about that? Either you handle it by yourself, but Pandas does it very conveniently and helps you with things that are not that rigidly organized. And we will see it's very useful. Matplotlib, of course, is like a standard still to plot things in 2D and 3D. This could be a very simple example where you say, I want to analyze the performance, the historical performance of the DAX index, and you see above just like the movement of the index, you see the crises, or the 2 crises, the big ones. The first, the bust of the new economy bubble, and the second one after 2008, the recent financial crisis. And below you see the daily log returns, positive returns and negative returns, of course. You see volatility clustering. And these are, for example, typical things you want to have when you analyze time series. And with Python, there are only a couple of lines of code when you have the data stored in Excel, where you just iterate over the rows that are in this Excel sheet. If you know where the data is placed, then you can generate a list of dates, for example. Also times. If you have high frequency data, of course, you would have liked to have times over a day. Then day is not small enough for the high frequency traders today. And you can generate the list with the quotes. And Pandas, for example, you see it over there, offers a number of very convenient objects like series and also data frames, where all the things happen that I mentioned before. There, Pandas takes care of the of missing data, for example, and really has a mechanism to attach the points to the right dates, so that, see it here, you don't have to take care of the x-axis, where you say these are years or dates, and you don't have to take care of which is to be placed where. And to generate such a graphic, you see only a couple of lines with Matplotlib. If you have another language, everybody of you is aware of it. It takes probably lots of code to generate it, but this is also everything that a student can learn over the course of a single semester course. And this is, for me, also something that is important because Python is, as I said before, very well suited to teach such stuff, not only to analyze things and to work with it, but also to teach and to learn these things. But you have also some more sophisticated things if you want to analyze time series in a scientific context. This, again, is done with Panda. But what you see here is like meta-statistics. You have functions to generate and to calculate rolling averages over time and so forth. What almost everything you can think of, you can do with Panda. Then you have correlation functions over ruling windows and so forth. And Pandas is doing all this, what you see here, with the same compactness, only with a couple of lines of code. You see it here. You have the rolling correlation between the mean return, which is rolling over 252 days, and it takes care simply of the attachment to the single points in time, because you see this starts a little bit out later, so the first period is missing, but it's no problem with Pandas. So it takes care of the missing data, it just adjusts the x-axis and so forth. In that sense, if you have to analyze time series, Pandas is a really good choice because it makes a lot of stuff convenient, building upon Numpy where these functions are missing. But I had a very interesting discussion at the lunch hour today, and there are still things going on where they want to put these functions into Numpy, into the core library, so that maybe in the near future, they've been talking about 6 to 9 months, you will have these time series, or a couple of them, the most basic ones, also in the Numpy library. Then, of course, you have the cross-section data. This is another picture. The first two pictures have been like time series. You have different periods of time. Here you have a single point in time, but lots of information about it. What this says, it's a little bit complicated. It's the implied volatility of a number of options. The input are option quotes that you observe at the exchanges, and via an optimization, you numerically calculate implied volatilities. These are very, very important inputs to value derivatives in general. So people at Quantdesk are used to work with these, and they are calculated, updated regularly, at least on a daily basis, sometimes many, many times over the day. And you have also to take care of these cross-section data. But let us take a brief look at the theory of derivatives analytics. So the most important is not the right. Well, maybe, let's say the first consistent model to value an option, call and put options, which can be exercised at a single date, has been published in 1973 by Black-Scholes, and simultaneously Robert Merton also published a companion paper. They worked together, and two of them, because the third was already died at that time, received a Nobel Prize for economics for discovering the formula which is behind this. But this model says mainly we have two assets traded in the market. The one is, for example, an index, like the DAX that we've seen before, and the other is like a riskless bond, is like a bank account. The DAX is, of course, risky. No one knows where it will develop tomorrow. There's uncertainty about that. This is represented by a Brownian motion, which is like a normally random figure. And the second one is like a riskless bond. You can go to the bank, and the bank says, okay, you get R% return per annum. This is for sure. There's no risk. You get it, and take it or leave it, so to say. And in this world, they showed that if trading in these two securities is available, you can replicate the payoff of the option. And if you replicate or can replicate something, then by arbitrage, the price of the replicating portfolio and the option must be the same. Because if you have the same payoff, the price for two things must be equal. So this is the fundamental thing behind it. So there is a closed formula for this. So what I will show next is not necessary at all. You don't have to simulate such a model, or maybe in a different context, but not to value a simple option. But for the simple option, which is my next example, you don't have to simulate it, but I think it's a very enlightening example because it's simple enough to understand the major workings behind it. And what we will do is, I will go to the next slide. You see equation 1, which is the one which has these, the uncertainty, the risk built in. There's a risk source, which is represented by the set as a Brownian motion. And we can discretize the stochastic differential equation to get a difference equation, where we are now arrived in a discrete time grid space, so to say. The first equation was in a continuous time setting, but in a computer it's very hard to build a model with a continuous time, so you need something that is discrete. And here's a discretization. You have a time interval of delta t, and you have this difference equation which tells you how to come from the value today to the value today plus delta t. So to say, the next step could be a day, could be an hour, or could be even a month, or whatever you choose to value your option. In my examples, when we have a 1 year horizon, you will typically have like 20 time steps, or you will have 50 time steps, for example, like a week over a horizon of a year. So the only thing you have to do is to make sure that you have standard normally distributed random figures, a random variable small set. And this is the source of randomness over there. If you have the pseudo-random numbers, you just have to put these into your difference equation, and then you can evolve your index stochastically. You can simulate it. So if you have done enough simulations of the index, for example, say 10,000 pairs, 10,000 simulation runs, then you get at the horizon T, big T, where you're interested in, you get maybe 10,000 of these realizations. And as I said before, the price of a derivative instrument is derived from the value of the underlying. So you have some kind of function h, it's the inner value function, which gives you exactly this connection where you not only have 10,000 STs, but you have also the inner value of the option at this state, and you can sum it up, average over it, and discount it back. There is a huge block of theory behind it, but this is a very, very brief summary just to get to what we want to see in the next step. The only thing you have to grasp here is that you simulate things 1,000 times, 10,000 times. You have a number of values at the end, you average over these, and you discount them back. And then you have the value. Graphically, it could look like this. These are only 20 simulated index levels. It doesn't suffice to have 20 simulations for evaluation. In order for the estimator to converge, you need 1,000, sometimes even 100,000 of simulated paths. So here's just to show what happens. You start at a point, here's 36 in the example, and there is a random evolution of the index, and this a couple of times. You also see the thick blue line, which represents the average over this. This is the drift R. On average, this says the index drifts with R, which is in this example 6% per annum. So let's come to Python. I think if you take a look, apart from the import of library functions, every student, or if you start out, this looks like mathematics. You just say that, for example, the strike price K equals 40. This has nothing to do with programming, but it's quite easy. It's short and it's dynamic typing. You don't have to take care of, or only to some extent, if you have K like 40 dot, or if you have K like 40. If you want to divide things and so forth, of course you have to take care. But even for students, as I said, it's easy to grasp what is behind it. Just like a couple of parameters, and they are defined. This has nothing to do with programming so far, just variable declarations. But if you come to the simulation, this is where we are now close to the main topic, the simulation step over there, index level path generation, where you just initialize a matrix. As I said before, finance is all about matrices, it's linear algebra. You initialize it with, or the first day, so to say, where you start off, for example, at the 1st of January in 2011. You analyze it with S0, which was defined before as 36. You remember the picture. All these pairs started at 36. Then you draw, for every time step, the required number of random figures. This is done with a single command, standard normal of I. Big I is the number of iterations. It's like 10,000 or 50,000. And then you go step by step and simulate the evolution of the index over time. And this is already time consuming. You could have done this, of course, or in C, you would have, or in C++, you would iterate twice, of course. You would iterate in the X and in the Y direction, and this would take pretty long in Python. I have also, I will show this shortly, a more compact implementation where you even can get rid of this iteration where everything is done in Numpy. But in order to retain some readability, I chose this example that you see that it's evolved step by step, but as a vector, step by step. So in the end, there you see the estimator. It looks pretty similar to the formula that we had before. You just discount the average of your inner values at the end, and you're done. This is the first pretty simple example of Python usage for Monte Carlo simulation. The standard book for Monte Carlo simulation financial engineering is by Klasserman, published in 2004. Starts out with a similar example, but there's an implementation in Excel. And it's, I don't know, it's like not very readable, and you have to take care of these cells. And if you just think of Excel, where you have to change the number of time steps, or you change the number of pairs and so forth, and it's. But if you would have started out with Python, I think much more people would have replicated it and understand it a little bit better. One step further. Evaluation of European option is not very involved. It's like what I showed there. It's not really necessary because I said there is an analytical, a closed formula available. You don't have to simulate it. But if it comes to American options, which can be exercised at any time over an interval, in comparison to a European option, which can be exercised only at the end of the interval, only at one point in time, the theory and also the implementation is a little bit more involved and more complicated, and you need to do a lot more of calculation and number crunching in comparison, because you have to solve an optimal stopping problem, which means, for example, if the option has a time to maturity of 1 year, you have to take a look at the option at every day and decide, should I exercise it or should I wait? Should I exercise it or should I wait? Should I exercise or should I wait? This is the everyday question that you have to ask, and it's not that easy to solve the problem. In a different context, different from Monte Carlo simulation, it is quite easy. But if you think of Monte Carlo simulation, if you think, for example, you have 10,000 pairs, we saw them, or just think of the 20 we saw in the picture, and you're riding on one of these pairs, then you don't know how to make the decision about exercising or not. Because if you are sitting on one such path, you don't know what happens tomorrow. You just have the information about the index level today. You don't know what happens tomorrow. Maybe if you have simulated, you can say, well, I use the information that my computer program generated for me because it's clear. On the next day, today we are at 100, and the next day, my simulation says it's 110. Yeah, but perfect foresight is nothing seen in financial markets, so I can't use this information in a valuation algorithm. If I would use it, I would make a systematic error. I would build in something that I don't want because I would overestimate the value of the option. So I need something different. But a little bit of background. The optimal stopping problem, which is a very abstract formulation to say, if I can stop the option at any time in the future, I take the supremum over the expectation of the payoff, overall stopping times that are available. This is a very abstract concept. But there's a very important result which says at any given time over the relevant interval, the value at time t is the maximum of the inner value, which is immediate exercise, and the value of weighting, which is an expectation, as defined below. So at any point in time, I know I can weigh, okay, if I exercise right now, I know for sure what I get. If I wait, it's unsure, but I have an expectation over it. And the problem of valuing the American option in this context is to get an estimate for the expectation. As I said, you are not allowed to use the perfect stuff in terms of if I'm sitting on this single path, I know what is on the next day. But what I can do is to get estimates by using the cross-section, to remain with the terms that I introduced earlier, to use all the information that I have at this date over all my 10,000 simulated paths, and regress the values that I see in the future against the index level today. So here is it formulated again. You have the problem, given at day t and path I, that you don't know the expected value. You only know the single simulated value and the solution that Longstaff and Schwartz proposed in 2001. It's not that long ago, it's just 10 years ago that they came up with this efficient algorithm, is to estimate the continuation values by ordinary least squares regression. Some kind of optimization problem. Where I said earlier, in finance, you more often than not need optimization techniques. And the algorithm is called least squares Monte Carlo. And in principle, our valuation suite decision is built around two things. It's Python and it's this algorithm. So these are the two main building blocks of what we are offering to our clients and users of the software. And just to make the point again, before 2000, so to say, there was no efficient algorithm available to value American options by Monte Carlo simulation. So there has been around an approach since the 70s with a different numerical method, but by Monte Carlo simulation, it's just possible since 10 years. It was a major obstacle, and it was also some kind of annoying thing because Monte Carlo simulation is very well suited for a number of things, but it was not suited, at least at that time, for American options. So there was like divergence, but with the invention of this algorithm, there was a whole new world for applications in terms of Monte Carlo simulation. But this also raised the bar in terms of computational power that you need in order to implement it, because Monte Carlo simulation in combination with all these regression things is computationally very demanding. How does it look like? Now we are again at the cross-section data sheet. It's generated with our analytics suite. At any given point in time, by simulation, you have these red dots, which are the real, that's the simulated continuation values. You have a number of these, like 10,000. But you can't use them directly, but you can use some kind of average. You can use a regression function to decide whether to exercise the option or not. If you have, for example, 50 time steps in your simulation, you have to do this 50 times. At every time step, you do this. And at every time step, and this is shown on the next slide, which is, again, a time series slide, it's over time. The algorithm works backwards, starts at the end, goes one step, two steps, three steps backwards, and always updates the information. So here you would say, for example, the upper yellow line, this will be the value of the option according to this path. But you see, the algorithm says, oh, well, I would exercise already earlier because I cannot foresee that it will rise that high. So I would exercise earlier and thereby I would, so to say, make a mistake on this particular path. But on average, you see it's coming down to really averaged value, and this is what Monte Carlo simulation should do. Here there's a real dispersion at the start of the option term. You see that these things are coming together and are more averaged. So this is how the algorithm works, and you can imagine this is the most simple example you can have. It's just like an American put option. It's the most plain vanilla stuff, and there are lots of things that are very, very complicated where you have, for example, 3, 4, 5, or even 10 sources of risk, where you have different features built in, where you have to take care of different time windows and so forth. And the algorithm and the demand for computational power becomes higher and higher and higher, and the algorithm more complex and more complex. How does it look like in Python? Once again, just the definitions of the variables for convenience. A number of little helper functions. You don't even need it in this. I will show you shortly a very compact thing where you have a random number generator. Here are some kind of variance reduction techniques, because you would always have a Monte Carlo estimator that converges very fast, which means that you can have fewer simulation paths in order to get good results. So this is meant by variance reduction. And if you have a number of these techniques available that you can use, the hope is that everything will be more accurate and more fast. So there are built in two types of variance reduction techniques, and they are very easy to build in Python. I cannot think of this implemented in C, C++. Of course, it's possible, but it would be, I don't know, a number of 10 slides just to present the code in order to do these two things, which are labeled AP and MM. AP stands for antithetic path, which means for every up step, I also have something that steps down, and vice versa. And MM stands for moment matching, where I just correct the random numbers in terms of mean and standard deviation, because the pseudo-random numbers from Python are not that good, but what I can easily do is just to correct the mean and the standard deviation in terms of having a 0 and a 1 afterwards, what I desire. So this is pretty easily done with Numpy. And afterwards, what you have already seen, the simulation step, where you have the step-by-step evolving simulation over time. And now we come to the regression step. If you want, I have some slides of these, but I didn't brought them. If I explain the Longsdorff-Schwarz or the least squares Monte Carlo algorithm in more detail, I have a number of slides just to explain the algorithm. But if it's implemented in Python, you only have 3 lines of code, mainly 2 lines. So I don't need to define the RG where the regression parameters are stored. So it's only 2 lines of code, but the algorithm described is like 3 to 4 slides just to describe the algorithm. So in Python, it's pretty compact. You can do it very easily, and the where command here from Numpy is also very convenient, such that you have very concise implementation. But what I want to show just as a brief demonstration in between is a little bit more compact implementation. This is mainly anything you need. You just have a couple of variables. You have the algorithm a little bit more compact. Here the simulation is done without any iteration. You need some finance behind it. I simulate mainly the logarithm of the stock and not the stock itself, so I can have addition instead of multiplication, and then I can add it up, so it becomes more compact and even a little bit more faster. And there I have only 2 lines for the whole regression step, where I have to iterate because I need the information from the optimization step before. Here I can't get rid of the iteration, but it's the only iteration that remains in here. Everything else is done on a Numpy level in terms of matrices and arrays. And you see here the regression. Maybe if I take just the 3 and I should show you. Here is the value 4.40. There are some other results. So this is what I meant by variance reduction. These are 2 other results from other valuations. You see that there is still a variance in the value that you get. Because you simulate, you always have simulation errors, simple mathematical errors, and you want to have this a little bit more compact, but I just used a couple of paths, so the convergence is not that good. But what I also want to show is, if you want to plot this kind of stuff, you can work with, for example, if you want to plot the first 10, for example, of these. It doesn't do it. Oh, well, it's actually what I wanted to show is the figure that you saw before. Just the 10 lines. You only need a single line of code just to show the first, for example, 10 paths or first 100 or whatever you want to see. Also for the others, so you see everything done here is quite compact, and it's also pretty fast in terms of speed. I will show some results briefly afterwards. There's one thing that I came across actually I think a year or 2 ago, where there was a paper published by Medvedev and Scalet, two researchers, and they analyzed the valuation of American options, which I showed you before, in the context of a rather complex model with stochastic volatility and stochastic short rates. And what they came up with was like an approximation formula, which is very easy and fast to implement. But this was not the point that I was intrigued by. It was more that they wrote that the MATLAB code implementing the algorithm of Longstoff-Schwarz, it's actually what we discussed just beforehand, takes dozens of minutes to compute a single option price. And this is, of course, nothing that you want to have in practice. So if a bank or a trader is sitting there and wants to value his or her option, she can't wait dozens of minutes for a single option price. And I tried just for myself how fast it can go with Python without any hardware optimization. The numbers I will present are just from this notebook, which is already 3 years old, though I was only hunting for orders of magnitude, not for the last tenths of second. And if you take a look at the Python results of our script, if we have a 25 time steps and 35,000 pairs, which represents more or less about 180 megabytes of data, which is not, well, which is much of data already for this simple setup. The data is crunched on this notebook in 1.5 seconds. And we get the same accuracy, which is, of course, a very important requirement. We can always say we get faster, but you need the accuracy as well, because, as I said before, it's all about money, and you should take care even on the decimal places and not only on the big numbers. So it's in terms of a comparable accuracy, where we reduce the time from dozens of minutes to 1.5 seconds. Even if we go to, let's say, 50 time steps and 100,000 pairs, then you have like already like 1 gigabyte of data to crunch. Thank you. And then it takes on this notebook 8.5 seconds, which is still something different as dozens of minutes. So the speed up in this particular example has been 480 times plus, but it is only to illustrate that it's possible with Python. But many people still think it's not, and they're using Python, but not for the core implementation of their algorithms. So, and what I also have to confess, in a sense, is that we used a little bit of a different implementation. So we just tweaked and optimized the algorithm. I had a conversation, or at least an email exchange, with one of these, a conversation about this, and I said, well, we had just like a brute force plain vanilla implementation, and it was like, I don't know, 500,000 pairs, and it was more like a brute force approach. And I said, well, of course you have the choice, and it's easily done with Python to add these two things that I showed before, for example, to have significantly improved convergence of the algorithm. Here are some things that was actually 1.2 seconds in this particular run, where we have valued 108 option prices, but it's just to back up what I presented before. So to the last path, we have a couple of minutes left. It's about our valuation suite. What I wanted to show with the first two parts is that Python is very well suited to implement derivatives analytics applications, but what we have done so far is really build a full-fledged derivatives analytics suite around Python with many thousand lines of code, which are of course a little bit different than the ones showed before, which are only examples and kind of prototypes, like algorithmic examples and not productive environment code. And what our suite can do already is to value a number of products. The universe of derivatives is not, unfortunately, not that simple as presented before, that you have like a European put option and a European call option, and in addition you may have an American put and an American call option. You have hundreds of thousands of different products traded in the market, and our approach was to have a very flexible modeling engine where you can build your models by yourself. You also have a number of standard models, but where you can model almost everything you can think of. And the whole logic behind is also done in Python. You have a number of underlyings that you can use. You can value options on indices, on stocks, bonds, interest rate, currencies, commodities. We also added variance and volatility as assets recently. So you can do already a lot of stuff. I don't want to say everything because there's too many products in the universe. And I think no one can do everything, but we can do already a lot. Where you can use it is mainly financial research, of course, where I use it at the university, but it's mainly targeted at the financial engineer, at the quant who is designing products, or someone who is buying such products in the market, like in hedge funds or in asset management companies. They buy the products from the investment bank, but also for insurance companies and actuarial calculations, for financial reporting. And this is also some kind of specific things, real options valuation. So just to say, there are a number of areas where you can beneficially apply our suite. It is built as a completely web-based application, typical LAMP architecture, where the P is, of course, Python. Numpy is at the very heart of it. Almost everything is, in terms of calculation, is done in Numpy. We also use Moi Wiki, which is Python powered. Everything you will find at our company is Python, Python, Python. Of course, for the web GUI, we need a little bit more, but the core, you can say, is completely done in Python. It's my last slide. Maybe I then have, maybe if the Wi-Fi connection works, I can show it real time. What my and our vision is to have a derivatives analytics suite which is to be seen like Google today if you think of information gathering and search. We've built a web-based application where you log in, where you have your screen, where you model something, where you can value, where you have graphical analysis, but it's not the typical way that quants and traders and so forth work in banks. You want to have it integrated in your very tool. For example, in Excel, which we already mentioned a little bit earlier, or you want to use it on your own website, or you want to integrate it any other front office application like a trading or portfolio system. And this is something we added in the first half of this year, or so to say last 4 or 6 weeks. We went live with it, where we have a complete web service-based valuation, where you only model stuff. You can have like 1,000 models on your server, and you can deliver variables, input data. You don't have to. The software can also take care of these automatically, but if you want, you can like have updates, for example, for the volatility. Here this example is in terms of an American put option on December American put option on a DAX, where you can deliver the volatility, where you have a rate, for example, and a strike, and you get back either in XML or in any other format you like, the information about this. So because, as I said, as fascinating as a web-based solution is, and as easy it is for us to take care of the web-based solution without any software distribution, people want to use it in their own environment. They want to implement it wherever they work, with whatever they work, be it scripting, Excel, or something else. And this has been a main step for us to get into this whole world. And also, as you see, everything is done in Python. The decision eval Python script is the one that takes care of what is delivered back. Yes, if we have a couple of minutes, I will try to show it. I have some minutes left. Or if there are questions at this moment, I'm pretty glad to answer them.
7 minutes left.
7 minutes. So if I just want to, because I was kicked out a couple of times beforehand from the Wi-Fi. I don't know if
we can try it on cable.
On cable. This, yeah, okay. The old technology.
Technology is the word we use for things that don't work correctly.
Yeah, it's a summary. Just let me check beforehand. irgendwie. So maybe it tries to repair it, the change, but I'm glad to take questions if you like. In the meantime, yes, there's one.
Do you sell your product just as a Python library that doesn't need any access to any web servers or anything like that? We could just drop it in and ask it for the price of a particular option? Or is it always tied to a web-based service?
It's always tied to a web-based service, actually. So you buy a license or you rent it on a monthly basis.
But
it's software as a service, so to say. It's not like a library that we sell as a Python thing. It's built on Python, but we don't distribute any code. So
if your server disappears, our business is down the chute hole.
So I didn't get that.
If we're asking your server for prices and you disappear off the internet, we're totally up the creek without a paddle. Is that how it works?
If I got it right, you said if we disappear, we sold the service and we disappear on the internet, then it doesn't work anymore.
Yeah, if somebody unplugs your internet connection or your power at your data center and we're using your software to value our portfolio, we wouldn't know how much it's worth.
Well, it could also be installed if there's someone who has a fear of it. It could also be installed on your own server.
Okay.
So if you want to take care of this, you can take this. But the standard, the cheap licensing model is just built on a regular service, and we have it in a professional data center with all that fire protection. I don't know what it is. It costs a little bit of money, but we don't do it ourselves, the hardware side. So it's hosted in professional service centers around. But if there is a bank or someone who says, well, I don't trust you, I want to have it on my own server, then there's, of course, the possibility to have it as well. So they have to take care of it.
Cool.
Yeah, but the question is, of course, a good one. If you need a price and the service is not working, what is...
I was wondering, have you considered porting this to CUDA or using PyCUDA or Theano, one of the GPU libraries?
Yes, we've been thinking about this since a couple of months, or say a year and a half, so to say, but so far we haven't done anything in this direction. Because the major benefit of CUDA is, of course, in parallelization. Mm-hmm. And the algorithm I showed you before is hard to parallelize.
I once saw a webinar about guys who embedded CUDA in Excel, and they got fabulous speedups, but maybe it doesn't...
Yeah, but if you use PyCUDA or something, then you have a very convenient access to Numpy and so forth. But what you need is the algorithms that can benefit from it. So if you have this regression over 100,000 of paths, you can parallelize it in terms of 2 times 50,000 paths, because you need the cross-section of information, this type of data. Then you have to, at one point, you have to get the data together, and then you lose everything in terms of coordinating. So
That's right. It might work for European option pricing. But
of course. This is where it is used extensively. But this is not our focus. Because our service is not, because it's built on Monte Carlo simulation, it's not very well suited for real-time pricing and for pricing huge books. So say 100,000 options in real time. This is what we can do. It's more for complex options for engineers, and they can wait maybe a second.
Right. Okay.
It's fast already, but not fast in terms of thousands of options per second.
Okay.
But it's very interesting. We are thinking about it, and in the near future, I guess, if the libraries become a little bit better, we will go the next step in this direction.
Would be interesting.
Yeah, of course.
I don't remember if the slides actually included this, but do you have a preferred data type that you operate on? I mean, single precision or double precision?
It's double precision, everything we do.
Okay, so...
You need it, in terms of convergence, you realize the differences.
Yeah, but that's a bit bad in relation to GPUs, because...
Yeah, but with the recent...
Well, but you can probably get something still.
At least as far as my understanding goes, with the recent releases of the new PyCUDA, or the NVIDIA cards, double precision should not be their problem anymore.
Still somewhat slower than single precision. But
I'm not an expert in that, but my hope was that it is somehow solved. But and you don't need it always, but it's better to have it. You don't know how things go and how convergent with this huge amount of data sets it goes. So you always want to have typically double precision data. Any other question? Unfortunately, the web is not working, so I can't. Unfortunately. So, thank you very much
Thank
for
you.
your attention.